With your permission, I think we should start now. You are not audible, sir.
Sir, More sir has left the meeting.
Yeah. Okay. Then we can start now, ma'am. So,
Sure.
yeah, I, Vaibhav Dabhade, on behalf of computer engineering, welcome you all to this session of machine learning and pattern recognition. Now, I request Dr. Kalpana Maitre, ma'am, please introduce our today's expert speaker, Dr. Prabir Vishwas, sir.
Sure,
What do you, ma'am?
yes. Can you hear me?
Yeah, ma'am. Yeah, you are audible. Please continue.
Good afternoon, respected dignitaries and participants. I take immense pleasure to welcome respected Professor Dr. Kabir Kumar Vishwas, who has been at the forefront to demonstrate his passion for the education community. He is working as professor and head of the department Electronics and Electrical Communication Engineering at IIT Kharagpur. He received his BTech, MTech, and PhD degrees in Electronics and Electrical Communication Engineering from the Indian Institute of Technology, Kharagpur in 1985, in 1989, and 1991 respectively. He served Bharat Electronics Limited, Ghaziabad as a deputy engineer during the period 1985 to 1987. In 1991, he joined the faculty of the Department of Electronics and Electrical Communication Engineering at IIT Kharagpur. He served as the head of the Computer and Informatics Center at IIT Kharagpur from March 2008 to December 2014. Professor Biswas visited the University of Hessen-Lanton, Germany during the March 2002 to February 2003 as Alexander von Humboldt Fellow. His research interests are in image and video processing, pattern recognition, multimedia system, etc. He has supervised 12 doctoral students and published more than 100 research papers in various reputed international and national journals and conference proceedings in these areas to his credit. He has prepared 4 online video courses under the NPTEL program. Sir also holds life membership of Indian Unit of Pattern Recognition and Artificial Intelligence in India. He is also a member of professional bodies of repute such as Institute of Electrical and Electronics Engineers, USA. He has served as a member of technical program committees of several national and international conferences and served as an organizing chair of Indian Conference on Computer Vision, Graphics and Image Processing in 2008. He is working on various sponsored projects sponsored by MHRD, Government of India, Department of Science and Technology, Indian Railways, SRIC, IIT Kharagpur. He is an editorial board member of International Journal of Medical Engineering and Informatics. So enough cannot be said about him. So let us directly welcome him and learn from his expertise. So I welcome you, sir. Now you can start your session, sir.
Thank you. Thank you for the nice introduction. I would like to share the slides which I will use for the presentation. I hope you can see the screen.
Yes, sir.
Yeah, good afternoon, everybody. I have decided to talk on this generative adversarial network, which is an efficient tool for data generation and data completion. Possibly today is the 4th or 5th day of this FDP, right?
4th day, sir.
4th day. So there must have been some introductory lectures on pattern recognition techniques, though I will briefly describe about what is pattern recognition, what are the features that you can use for pattern recognition. In brief, just to set the tune of what is generative network, where the generative network can be used, and then what is generative adversarial network. Okay, so let us start. So I'll start with what is machine learning as such. So you find that when we talk about machine learning, what we have at the, if I take this machine learning unit as a black box, at the input we have different kinds of signals. Then from these signals, you compute what is known as descriptor or features. A number of features taken together is known as feature vector. All these things you have, I hope you have done already. Then these feature vectors, the feature vectors which are derived from known objects or known signals, they are used to train the classifier or the recognizer. So there we can have different types of classifiers, like Bayesian classifier, we can have support vector machine, we can have linear machine, we can have neural network. And in today's scenario, what people are talking about is deep learning or deep neural network. So these are the things which have to be trained. So these classifiers have to be trained using the feature vectors. In case of deep learning, of course, we don't talk about feature vectors separately, but you feed the signal directly to the network, and the network learns under supervision. So this is a kind of learning which is known as supervised learning. So once the network learns from the either from the feature vectors, or in case of deep learning from the signal itself, that which feature vector belongs to which class, or which vector is derived from which of the objects or patterns. So once the classifier is knowledgeable about that, then the next step is deployment of the classifier in your application domain. So when you deploy, forgetting about the deep neural network for the time being, let us talk about the traditional machine learning or traditional recognition problems. Where given an input signal which is unknown, I need to classify to which of the class that signal belongs, or I want to recognize what that signal is. That signal may be speech signal, the signal may be image, the signal may be, say, output signal from certain plant, or whatever it is. So I have to extract the feature vectors from that unknown signal, as we have extracted the feature vectors for the known signals for supervision purpose. These feature vectors are fed to the classifier, which are already trained. And the classifier, whatever classifier it is, it will tell you what is the class of that signal, or what is that signal. In effect, and this is the same thing that we have also learned from our childhood. So during the childhood, our mother or father told us A for apple, B for ball, C for cat, and all that. And every time they have shown us the letter A and the corresponding object apple. And these A and apple, they were shown multiple number of times. It is not that you have been shown once and you have learned what is A or what is B. It has been shown, if you remember, many of you might not remember. At least I remember, because I got a lot of scolding from my mother, because I was not being able to remember what is A and B. So this was shown multiple number of times in various ways, either from the book or handwritten character, on a slate or a paper. Different time you write the different same letter A, it will have different style. No two instances of A written by the same person can be identical altogether. So we get the signal in various forms, with distortion, without distortion, and from those examples we learn what is A or what is B. The same concept is applied here in machine learning or pattern recognition cases. So let us just briefly talk about what is this feature or feature vectors that we are talking about, or the descriptors that we are talking about. Let us take a simple example. Suppose I want to distinguish between a horse and a zebra, right? Now you find that if I look at the shape of the horse and the shape of the zebra, you find that in both the cases, both for horse and zebra, the shape is almost similar. So just by looking at the shape, maybe using this shape, I can distinguish a class of animals from another class of animals. So from this shape, I can simply say that, okay, this is an animal which is definitely not bird. This is an animal which may be a horse or maybe a zebra. But to identify whether this animal is a horse or a zebra, this shape information is not sufficient. I need something more. So what is that something more? That is what is known as your region feature. Okay, so you come over here, you find that within the region, bounded by the boundary of the horse or bounded by the boundary of the zebra, the region properties are different. So in case of horse, if you look at this, its color is different, its texture is different. Whereas over here, when I talk about a zebra, this has black and white stripes. So you have different color, you have different texture. So when we talk about, so mostly I'll take examples from the animals, right? Because my domain is computer vision or image processing. But whatever I talk today, the same is applicable to speech recognition, the same is applicable to speaker recognition. Only difference will be your low-level processing tasks. That is when we talk about computer vision, the input signal is an image. So the feature extraction techniques, which are the low-level processing tasks, they are image dependent or they are application domain dependent. But when we talk about speech signal for speaker recognition or speech recognition, the signals are time domain signals. So there my low-level processing task and the feature extraction techniques will be different. But once you extract the features, what you have is the feature vectors or the descriptors. And that point onwards, your classifiers are all same. Only thing is you are training the classifier with the feature vectors. The feature vectors are domain dependent, but the classifier is not domain dependent. So if I train the classifiers with speech signals, the classifier will tell me different speeches or it will tell me different speakers. If I train the classifier with images, it will try to recognize the objects. Okay. So given that, you find that, so in addition to the shape features like this, we also need the information of the region features, and the region features are maybe intensity, maybe color, maybe texture, and all that. So there are different techniques for extraction of shape features. There are different techniques for extraction of region features. Right. So to talk about how the region feature is extracted, say for example, I want to extract the intensity feature of the bounded region. So all of you know that we can have something called histogram of the intensity. What it says is, typically when we take normal images for commercial purpose, the images are actually 8-bit quantized, assuming the images are black and white or color images. So when it is 8-bit quantized, that means every point in the image or every pixel in the image is quantized by 8 bits. That means it can encode an intensity in 256 levels. 2 to the power 8 makes 256. So I can have 256 levels of intensity values that vary from 0 to 255. So all of you know that this histogram actually tells you that how many pixels in the image you have with intensity value 0, how many pixels within the image you have with intensity values 100, how many pixels with intensity value 200, and so on. So that is what is histogram. Now, if I normalize this histogram, that means sum of all these numbers of different intensity values, they sum up to 1, what I get is a probability density function. That is, what is the probability or what is the frequency at which an intensity of level, say 128, appear in the image. So once I represent this histogram as a probability density function, then I can extract the different shape information from this histogram. The shape information may be different statistical moments, maybe the second order statistical moment, and you all know that second order statistical moment is something equivalent to variance. So that tells you whether the histogram is a flat histogram or the histogram is a sharp histogram. So if the histogram is a sharp histogram, the second order moment will be low. If the histogram is a flat histogram, then the second order moment will be high. Similarly, I can extract third order moment. The third order moment tells you what is the skewness of that histogram, whether the histogram is skewed towards low intensity values or the histogram is skewed towards high intensity values. Say, for example, here in this particular case, you find that I have large number of pixels with lower intensity values because this image is darker, whereas I have smaller number of pixels with higher intensity values. That means this histogram is skewed towards left. Whereas if I simply flip it around a vertical axis, so that this region comes to the right and this region comes to the left, its third order moment will be different from the third order moment which is computed from here. But the second order moment, which is equivalent to variance, as I said, will be same for them, right? Similarly, I can compute statistical moment of order 4, I can compute statistical moment of order 5 and all that. So if I compute large number of such moments and arrange that moments, concatenate that moments, what I get is a feature vector, whereas each of this moment is one descriptor of computed out of this histogram. That gives you some sort of information about the intensity distribution of the image. Coming to the next one, suppose I have a color image. So you know that color image has got 3 different planes: red plane, green plane, and blue plane. So I can consider each of these planes to be individually a black and white image or an intensity image. You get the color interpretation to harder, but the images are nothing but intensity images. So given that, for each of the image, I can compute, or each of the planes, I can compute the histogram. So likewise, given this is what is your red histogram, this is the histogram of the green plane, and this is the histogram of the blue plane. For each of these histograms, by normalization, I get intensity distributions, probability distributions of intensity of the corresponding plane. And once I have this probability distribution, I can compute all those statistical moments for each of these individual histograms. And all these moments can be concatenated together to give you the descriptor of the color. So these are just 2 forms of descriptors or region descriptors that you can compute. Coming to the texture. So this is what is a texture. I can have different kinds of texture. So the shirts or sarees that each of you are wearing, each of them have different texture. But how do you define a texture? Definition of a texture is very, very difficult. But texture exists. I can distinguish from one texture from another texture. So that clearly means that I should be able to generate descriptors out of these textures, so that using those descriptors or using the features, I can separate out one texture from another. So these texture descriptors can be obtained both in the spatial domain, that is considering the images themselves, or the texture descriptors can be obtained in transform domain, that is you compute some transformation of the given texture image, and from the transformation coefficients, you can compute different descriptors or different features. So in image domain or in pixel domain, if you compute the texture descriptors, then one of the very popular way is by using what is known as co-occurrence matrix. The co-occurrence matrix says that I take a pair of intensity values which are placed at certain spatial locations with certain orientation. Say, for example, I want 2 intensity values. Say one is intensity value 5, other one is intensity value say 20. I want that how many times 2 pixels, one having intensity value 5 and other one having intensity value 20 at a distance of say 2 pixels apart and oriented at an angle of 45 degrees. How many times within this texture I have such pixel pairs? Okay, and this can be done for every possible intensity pairs. That is what is known as co-occurrence matrix, and this co-occurrence matrix can be computed for different spatial relations. For every spatial relation, I have a co-occurrence matrix. So you see that once I have this co-occurrence matrix, which tells you that two intensity pairs with certain spatial locations, how many times they occur within the given image. And as we have done in case of histogram, if I normalize this co-occurrence matrix, what I actually get is a joint probability distribution function. Joint probability distribution function given a certain spatial duration. So once I have this joint probability distribution function, then I can compute different types of features or descriptors from such a joint probability distribution function. Like I can compute what is the maximum probability of occurrence. I can compute something called element difference moment. I can compute something called inverse element difference moment. I can compute what is the uniformity. I can compute what is the entropy. So these are the different kinds of descriptors that you can compute from a co-occurrence matrix once it is normalized to give you a joint probability distribution function. Okay, and if I have n number of such co-occurrence matrices, from each of the matrices I can compute these quantities. So if I have m number of quantities and n number of co-occurrence matrices, I can compute m into n number of descriptors of features. So given multiple type of textures, maybe some of these features will be same over all the textures. At the same time, there will be some features which are different for different textures. So when I put them in the form of a vector, some elements in the vectors might be same or similar, but there definitely will be some elements in the vectors which are distinguishing elements or distinguishing features or descriptors using which you can discriminate among different textures, right? So these are the different types of region properties that you can compute from a given image. So I have two types of descriptors. One is the shape descriptor and one set of descriptors which are region descriptors. So just to describe an object in the visual domain or in an image, you make use of both. You concatenate the descriptors that you have obtained from the shape and the descriptors that you have obtained from the region properties, the region features, concatenate together to have a feature vector. And once I have this feature vector, so these are the other in the transformation domain, how we can compute the region features. So again, what I've shown is one transformation, which is wavelet transformation. And you all know that wavelet transformation actually breaks the image into different frequency subbands, right? So I can have information at lower resolution. I can also have information at higher resolution. And in each of these subbands, if I compute the energy and put these energy contents in a particular order, I get a vector computed from the wavelet transform coefficients. And this vector is again likely to be different for different textures. The other kind of transformation, which is very, very popular, and it has been very, very successful for obtaining texture description, is what is known as Gabor filter. So if you look at Gabor filter or the Gabor filter kernel, the Gabor filter kernel is given like this, where this x prime and y prime, they are actually rotational transformation, right? So x prime is equal to x cosine theta plus y sine theta, and y prime is equal to minus x sine theta plus y cosine theta. This is actually a coordinate transformation. So what this Gabor filter gives is, you'll find that this Gabor filter, this particular exponential part, this is nothing but a Gaussian envelope in 2D, which is modulated by a cosine wave, and this cosine wave is in the direction of x prime. So how many parameters I have? I have one parameter that gives me the rotation theta, another parameter that gives me the frequency omega. Other parameters are sigma x and sigma y, which tells me at what scale I want to compute the features. So there are set of such parameters, and different combinations of these parameters gives you different Gabor filter coefficients or give different Gabor filter kernels. And if you convolve your image with these different Gabor filter kernels, you get different output. Just like here, what is shown is this is a cosine which is oriented in the horizontal direction. This is a cosine which is oriented in the vertical direction. And this cosine is actually modulating a Gaussian envelope. So if I convolve this image with this kernel, this will be the output. You'll find that this output is rich in vertical edges. Whereas if I convolve this image with this kernel, this is the output, and you find that this output is rich in horizontal edges, right? So depending upon what kind of texture we will have such edge informations oriented in different directions. So this energy from outputs from different Gaussian, this Gabor filter outputs will be different for different textures. So that also gives you a discriminating power. So as I said, that if I combine all these different features, I get a feature, right? Now, these are the feature vectors which are known as handcrafted features. Now, why these are called handcrafted features? Because I have decided that what are the descriptors or what are the features that I am going to consider for classification purpose or for recognition purpose, believing that my brain works using these features. But is it true? That's a debatable question. Let us come to this. I have these two images, one on the left, one image on the right. Can you recognize these two images? Possibly yes. You will say that the image on the left is cave painting in Ajanta caves, and image on the right is Parliament building in New Delhi. How do you recognize? Answer is very simple. Visit those places and have seen these painting, particular building, Parliament building yourself with your eyes, or I mean, I have visited Ajanta caves only a few years back. But before that, I knew that this is Ajanta cave painting. How? Because in my history book, this painting or this image was shown and the caption was given Ajanta cave painting, right? And I have seen it multiple number of times. And from that knowledge, of course, I was talking about supervised learning. There is nothing but supervision. I've seen the images with captions. And by looking at the images, I have created some description or some model of the image, and this model is stored in my brain. So next time, a similar image shown to me may not be the same image, but another image from Ajanta cave painting, from Ajanta cave. If that is shown to me, I'll be able to guess, okay, this is something which is similar to that painting which I have shown, which I have seen before. So it must be something, some painting in Ajanta cave. But can you really say that exactly what feature we are looking into this to recognize that one is Ajanta cave, one is Parliament building? Is it that I'm looking at the edges? Is it that I'm looking at the color? Is it that I'm looking at the texture? Or what is it? Possibly a combination of them, or maybe none of them. What I'm looking at, I don't know. I mean, to be frank, based on what characteristics or what description I have distinguished or have recognized these images, I don't know. But I'm doing it somehow. Had it been so, then the same image, the same painting, Ajanta cave, and the same building, if they are shown in black and white, no color information, still I'll be able to recognize. So is it that I'm using any of the color information? Or if they're blurred, you pass them through a low-pass filter, it gets blurred, the texture information is almost lost. I'll still be able to recognize. So what is it that I look for to recognize these objects? That's a big question. So that is the reason the features that I have talked about so far, they are known as handcrafted features, believing that those are the features that we look for while recognizing an object or while recognizing an image. But that may not be true. But the fact is they work. At least they give you something, some descriptor, and using those descriptors, you can discriminate among different types of images or among different types of objects. So they work. But a more intelligent way is that let the machine decide that what descriptor or what feature best describes that particular object. So I come to a network, a neural network, which is known as autoencoder. So you find that in this autoencoder, there are two layers. One of the layer is called input layer, the other layer is called output layer, and in between we have a layer which is a bottleneck layer. So this is what is my bottleneck layer. Here the concept is you feed in a signal, say X. The network, I expect that it will reconstruct the same signal X, but while doing so, the information will pass through a bottleneck layer where the number of nodes in the bottleneck layer is much less than the number of nodes in the input layer and the output layer. Obviously, the number of nodes in the input layer has to be same as the number of samples that I have in the original signal. So if it is an image, and if my image is of size 10 by 10 pixels, I have 100 pixels, so I have to have 100 nodes in the input side. Similarly, I also have to have 100 nodes on the output side because I want the same image to be reconstructed back by this network. And while doing so, when the information is passing through this bottleneck layer, where the number of nodes is much less, it is expected that bottleneck layer will generate a description of this image, and this part, that output layer, should be able to reconstruct the same image using this description. So basically, in the bottleneck layer, what you are getting is you are getting a compacted representation of your input signal. And this compact representation using this, the decoder is able to reconstruct the image. That means here, whatever is being stored, that compact representation is sufficient to represent your original signal. So you find that here, your handcrafted feature has not come into picture. So whatever is learned by this middle layer or bottleneck layer, I can consider that to be the descriptor of the feature vector, and this feature vector can be used for recognition purpose. So there comes the question of how do you train this network? While training this network, as I said that I'm feeding an input signal X, I expect the output signal X hat to be same as X. So if the network is not able to reconstruct X hat, which is close to X, then I get an error, which over here is shown as a loss function, LXX hat. And for training the network, we use the gradient descent procedure using the backpropagation technique to modify or to update the connection weights in such a way that your error gets minimized. Okay, and that is how your network is trained. And once the network is trained, what I am interested in is just this part, because my network is not for reconstruction. But mind you that my topic is generative network. So when I come to this generative network, my basic interest will be in this part, not in this part. But for classification, we are interested in this part, because given a signal, we should be able to get a feature vector. The feature vector you can read using which I can recognize the signal or I can classify the signal. So if you look at that, what are the features that are actually learned by this network? What you can do is, as you know that the features are encoded within the weight vectors over here. So these weight vectors, if we display in the form of images, then these are the images which we get. So you find that what this network learns after the training is complete is different edge information, different corner information. The edges are oriented in various directions. Okay, the different intensity distributions and all that. And it makes a combination of all these features to generate your output. So these are the features which can now be used for the classification or recognition purpose, right? So still we are in the supervised learning domain, but what we have avoided is instead of using handcrafted features, we have given this responsibility of selecting the features to be used for classification or recognition to the machine itself. Okay, so the machine decides that what are the features that we can use for recognition purpose. So for using this as classifier, what we want is we will simply discard this output part, which is known as decoder part of the autoencoder. This is a portion which is known as encoder part of the autoencoder. So for classification purpose, we are interested only in this encoder part. So what you get out of this bottleneck layer is the feature vector, and it is this feature vector that is used to train your neural network, and it is this feature vector, neural network or any other classifier, and it is the same feature vector which is used for classification purpose. So this encoder gives you the feature vectors, which in the previous case, it was handcrafted. So we had to write algorithms to extract the feature vectors that we decided will work properly. Now this task is given to the encoder. I have Bayesian classifier, I can have support vector machine, I can have neural network, I can have linear machine, I can have RBF network. Different types of classifiers can be there for the classification of the recognition task. So what does these feature vectors actually represent? Why using these feature vectors your classification or recognition is possible? You find that when I talked about the feature vectors, whether those are handcrafted or machine generated like in autoencoder or encoder part of the autoencoder, right? I have a vectors having, say, D number of elements. So when you extract these feature vectors, effectively the operation that you have done is you have made a transformation of your input signal from the spatial domain or the time domain to the feature domain, right? So whatever be the dimensionality of your input signal, that signal has been represented by a D-dimensional vector, which is a feature vector. And if I think of a feature space having D-dimensional space, a feature space having D dimension, this vector is represented by a point in that D-dimensional space, right? So every pattern or D-dimensional space. And considering that the pattern is now represented by a point, my classification or recognition problem is very, very simple. The reason is, if I have two different objects or two different patterns, even by considering the intra-class variation, because no two patterns in this world can be exactly identical, there will be some variation. It is same as when you draw an engineering drawing. All of you have done engineering drawing. When you give a dimension, suppose I want to make a ruler of length 1 meter. How do you give the dimension which will go to the fabricator for fabricating that ruler? Do I simply mention 1 meter or I give something else? If you remember your engineering drawing class, you'll realize that I don't just give 1 meter. I give 1 meter plus minus some delta. That delta, that is the tolerance. This is the tolerance of manufacturing. This is the tolerance which is given by the machine. The machine is never perfect. It has certain tolerance, right? So that is the reason that no two objects, even if they belong to the same class in this world, can be exactly identical. So obviously in that case, even the feature vectors will not be identical. But if two objects are similar, they belong to the same class, the feature vectors computed out of those two objects will be similar but not identical. So that tells you that if I have two feature vectors or 2 points in my D-dimensional space, where the distance between these two objects is small, I can say that these two patterns are similar or they may belong to the same class. But if I have two feature vectors coming from two different classes or two different objects, then the corresponding points in my feature space will be far apart. So the distance between these two points will be quite large. So if the distance is quite large, then I can infer that the patterns that these feature vectors represent, those patterns are not similar, but they are different. Okay, so that is how I can distinguish between these patterns. But to make the job simple, in that case, what I have to do is I have to always compute the distance, right? Or if there are 1,000 patterns that I have used for training my neural network for a particular class, so I have 1,000 some points representing a particular class. And I have one point which is to be recognized, then I have to compute the distance, 1,000 such distances from each of these points, right? And if I have n number of classes, then I have to compute n into 1,000 number of distances. From there, I have to compute which is the minimum, and based on this minimum, I have to classify that particular object or that particular pattern to one of these classes. Of course, there is one such classification technique which is known as KNN classification. You might have heard about it, okay? Or nearest neighbor classification. But a simpler approach will be that if I can have an analytical model, so that for every class, I can have a function given an unknown vector, I compute that functional value, and for whichever class the functional value is maximum, I'll recognize or classify that particular unknown object to that particular class. Okay, so that is where your distribution of the feature vectors comes into picture. So here I give a hypothetical example that suppose I'm considering a two-dimensional feature vector. That is, my feature space is two-dimensional space. And I have different kinds of images. So this is an image of a bird. I compute the feature vector of this image, and the feature vector falls somewhere over here. I get another bird, compute the feature vector of this, the feature vector falls somewhere over here. I compute another bird, the feature vector falls somewhere over here. This is another image, car, whose feature vector should not be similar to this. So this feature vector falls somewhere over here. This is another car. This feature vector falls somewhere over here. This is a dog. This feature vector falls somewhere over here. This is another dog. This feature vector falls somewhere over here. So if you compute this way, you'll find that I have a number of images of birds. So all these feature vectors form a cluster. I have number of images of cars. All these feature vectors forms a cluster. I have number of images of dogs. All these feature vectors form a cluster. Clusters of the feature vectors coming from a particular class, they are compact. Whereas cluster of feature vectors coming from objects of different classes, they are wide apart. So this is what is known as distribution. And while computing this distribution, if I am considering the class of the objects as well, then this is what is known as class conditional probability distribution or class conditional probability density function. Okay. So mind you that I can just infer a very simple sort of classifier from here. What is that? I have all the feature vectors belonging to dog lying in this cluster, all the feature vectors belonging to car lying in this cluster. If they are linearly separable, I can draw a straight line from this region, okay, in between these two. So given an unknown feature vector, if I find that that feature vector falls to the right of the straight line, then I will classify that to be a dog. If it falls to the left of this straight line, I will classify that to be a car. Okay, a simple sort of classifier that I can make, a simple sort of a function. Okay, but that is too simple. This shows what is that class conditional probability density function that I have just said. Okay, now from there I can have different types of classifiers. One example that I have just given is what is known as linear classifier. I can have nonlinear classifier. I can have probabilistic classifier. That is, once these distributions are given an unknown feature vector x, you find out for which of them the probability density becomes maximum. I can compute p of x given omega 1. I can compute p of x given omega 2 coming somewhere over here. I can compute p of x given omega 3 coming somewhere over here. I can compute p of x given omega 4 coming somewhere over here. And out of that, whichever is maximum, I classify my input feature vector to that corresponding class. And this is what is known as likelihood maximization. So when I compute the probability density, this probability value, this simply tells me what is the likelihood that this object of this pattern belongs to this particular class. And when I go for maximization of this, it becomes a likelihood maximization problem. And using that, I can have a classifier. Okay, I can have a base classifier, which is a statistical classifier that again works on this probabilistic model. But I'm not going into all that details. I hope those have been discussed by other resource persons in this particular workshop. Now, what are the challenges? See, one of the challenges viewing angle. There is a Taj Mahal. I can look at the Taj Mahal from various angles, from various distances. So the appearance will be different. But all of them are Taj Mahal. So my recognizer or classifier should take care of all these different possibilities. They can be of different poses. I can have cat, but these cats are in different poses. This is another challenge, that my classifier should take care of these poses also. Illumination variation. I can have the same object, but while imaging, the illuminations are widely different. Intra-class variation. These are all chairs. Okay, I will agree this is a chair, this is a chair, this is a chair. But who will agree that this is a chair or this is a chair? Right? But I can have such intra-class variations. I can have distortion or occlusion. Maybe the objects are not fully visible. They are occluded by some other object. So the objects are partially visible. So your recognizer has to take care of this also. So these are the different challenges that we have for recognition. Well, so I'll just talk about machine learning versus deep learning. So this is a neural network model that you all of you know, that it has different layers. Every layer computes some function, right? So this layer 1 gives you function 1, layer 2 gives you function 2, and so on. And if I feed an input x, at the output of this layer, I get f1x, at the output of this layer, I get f2x, and so on. And finally, I get fkx. In each of these layers, along with the activation, we have some activation function, which are usually nonlinear. So what you have is what you vector you are getting from the previous layer, have a linear combination of them, and then pass it through a nonlinearity. Why nonlinearity? Because nonlinearity can take care of various complex situations. So you can model a complex nonlinear function using such neural networks of so many layers, right? Now, if this neural network is only for classification purpose, what I can do is I can feed in the feature vector that we have said earlier. Neural network gives me an output that to which class that feature vector belongs. That is what is my traditional machine learning approach. Whereas in case of deep learning approach, what I want is, we have seen before that I've taken an example of Gabor filter, right? So given an image, if I convolve that image with different Gabor kernels, I get different outputs, and from those outputs I can compute the features. So it is nothing but a convolution operation which is used for feature extraction. So the same functionality can be integrated in the neural network itself. So now the neural network can have two different functional compartments. One compartment can be used for computation of convolutions or the features, and the other compartment can be used for classification, right? So the first part is known as CNN, or convolution neural network, and the second compartment is what is typically known as MLP, or multi-layer perceptron, which is a traditional neural network used for recognition of classification purpose. So I can have these different layers. I'm not going to details of this. I can have convolution, then nonlinearity, then one is operation known as pooling. So this pooling gives you a property of local to global descriptors. Okay. And then we have fully connected layer, which is nothing but MLP, or multi-layer perceptron, which is used for classification. So this is the portion. Here what you are doing is, to the neural network, you are feeding the image directly. And for supervised learning, we are saying that, okay, this is an image of a dog. And the class output, I should get the dog output high, all other outputs low. If it is different, then you have an error. And you minimize this error by flowing the error information backward using your gradient descent approach and the same backpropagation line. Okay, this is what is your CNN or deep neural network architecture. So a deep neural CNN architecture typically looks like this. You have a number of convolution there along with nonlinearity. Then you have pooling there. You can have a number of them. Finally, I have a fully connected layer or set of layers known as MLP, which is used for classification purposes. So these are just different examples of this deep neural network that we can have. Okay, so we can have GoogleNet, we can have LeNet, and if you are aware, these are the networks which own that image net challenge problem. Okay, in different years. I'm not going into details of this, but what I was talking about that I want to introduce what is this generative model and what are things that we can do using this generative model. So far, whatever we have discussed, that is what is discriminative model. That is, this classifier is actually used to discriminate among different patterns or discriminate among different objects, right? But generative model tries to generate the pattern. So this is what is discriminative model. Okay, output of the network. So after learning, after training is over, this model, the discriminative model, actually learns the P of omega I given x. Okay, that is what is learned by discriminative model. But in case of generative model, we will try to learn what is P of x, not P of omega given x or P of x. Okay. So why this generative model? It was told by Richard Feynman that what I cannot create, I do not understand. The logic is very simple. If I really understand something, then I should also be able to create it. So whether I can create something using the deep neural network or deep learning model, and that is what is generative. So how it works? You collect obviously a large amount of data in a specific domain. Suppose I want to have a network which can generate human faces, realistic human faces, right? Not a sketch. What I have to do is I have to collect a large number of face images, train your network using those large number of face images, and then once the network is trained, it should be able to regenerate a facial image. Now, this facial image need not necessarily be one of the images using which the network has been trained, but it can be any other image. But only constant is that image must be realistic. Looking at that image, one should say that yes, this is a photograph, this is not a painting, right? So you train your network, your generative model, using those large number of images, and the purpose is that I want that network to generate an image like that, not one of those images, right? So that is what is the purpose of generative. Right. So how this generative model works? If I give a set of descriptions, say for example, when I talk about feature vectors, whether the feature vectors are handcrafted or the feature vectors are generated by the autoencoder. Every component of the feature vector gives you some attribute of the signal or some attribute of it. It may be an edge information, it may be orientation of the edge information, it may be color information, it may be texture information, all those things that we have said, right? So every component of the feature vector gives you some attribute of your input image, of your input object. Okay. So in case of generative model, if we say that I have an animal, I want to generate an animal which is big. So the size of the animal, whether it is big or small or of medium size, that is what is an attribute. Similarly, another attribute is number of legs, that the animal has 4 legs. Another attribute is ears. The animal has big ears. It has a long trunk. It has a pair of tusks, right? So if I give such a type of or list of attributes to my generative model, you see that using these attributes, can you guess which animal that we are talking about? Anyone can unmute yourself.
Elephant. We are talking about elephant.
Exactly. We are talking about an elephant. So how do we know that? We have seen large number of animals and we know that these are the attributes which are present in an elephant, right? So we want that the generator model should also act like this, right? But is it possible using the features of the feature vectors that we have talked about so far? Possibly not. So these are the variables which are known as latent variables, and the vector that you generate is known as latent vector. It is similar to your feature vector. Now, and why we are making this difference, I'll come to that a bit later. So what your traditional autoencoder or the feature vectors that we have talked about that has done is, for every attribute, we have computed a numerical value. So as for every attribute, we have computed a numerical value. That means this attribute forms a point in my feature space, right? And what does the decoder do? It takes that vector, that feature vector or latent vector, and then regenerates the same output, right? My generator model should not be like this. What is the problem in this model? The problem in this model is, so these are the feature vectors which are generated from the images from INNIST database. We are not going to that. But this is just a two-dimensional case, assuming that we have two-dimensional feature vectors. The autoencoder has generated all these feature vectors. And you find the problem with these feature vectors is that if you look over here, the feature vectors are sparse. Every feature vector corresponds to one of the instances of that image that this encoder has come across, right? There is no point over here. So if I sample a vector from this and feed it to my decoder to regenerate the image or an image something like this, the decoder, it is most likely, it will generate an image which is meaningless because the decoder has never seen this particular example. Whereas, if I can make a compact representation of these feature vectors, or if I want that whatever the encoder has done, so this autoencoder, instead of learning the feature vector themselves, if I can make the autoencoder learn the feature distribution. So once it learns the feature distribution, the space is continuous space. So if it can learn the feature distribution, I can sample a feature vector, I can sample a latent vector from that distribution, and now because it is a continuous space, feed this latent vector to your generator. The generator knows that it is coming from this particular space, which is continuous. So maybe I have not seen this example before, but I have seen an example which is similar. So I can generate an image or an example which is similar to that. I find that some questions are being asked. Let me finish this. I'll take up the questions one by one, right? So I want that something like an autoencoder which will learn not just the feature vectors, but it will learn the distribution of the feature. And that distribution is a continuous distribution. And the space will be a compact space. Okay, so if I do that, then possibly my generator will be able to generate the images. Okay, I will skip this. So effectively what I want is that the space should be something like this. Say for example, if I have these three images and one of the attribute is a smile, right? So you find that over here, this boy, he's not smiling at all. What the autoencoder will generate is a set of vectors where the value of this attribute smile will be a single value, right? This fellow is not smiling at all, possibly he's sad, so the value is negative. This face, Mona Lisa, it is neutral, right? So the value will be 0. This fellow is smiling a lot, So this attribute value will be positive. It will have a higher value. This is what my autoencoder will do. But what we want is not just a single value, but we want a distribution. So we want, maybe the value is somewhere over here, fine, but there should be a variation around that specific value. Similarly, over here, the value may be around 0, but there should be a variation. Over here, the value may be positive, but there should be a variation. So that you find that if I sample somewhere over here, I don't get anything. But if I sample somewhere over here, I get a definite value, right? So that is what is an encoder, autoencoder, which is known as variational autoencoder. Okay, and this variational autoencoder has to be trained in such a way that it does not learn just the feature vector, but it learns the distribution, right? And typically the distribution that we'll talk about is a normal distribution. That means this variational autoencoder has to learn the mean vector and the variance. Okay. So I'll skip this. I'll also skip this. Yeah. Right. So let us come over here. So when we talked about this autoencoder, what we said is the way we have trained the autoencoder is you feed an image, your autoencoder gives you output as an image. You train the autoencoder in such a way that the error between your original input image and the reconstructed image, that is minimal. Right? So that is what is known as data loss. But in this case, we want to learn a distribution. So using data loss, what I have is a compact representation of the image. That means I'm computing a feature vector in the middle layer. But here, as I want the encoder should learn the distribution, so just the data loss is not sufficient, right? I want that this distribution should be compact. At the same time, they should be very close to a target distribution. And in variational autoencoder, this target distribution is usually taken to be 0 mean Gaussian distribution. So here the different cases that you get, if I use only the data loss for training the neural network, for training the encoder, these are the distributions that you get. So you find that this distribution for samples from one class, this is distribution for samples from another class, this is distribution for samples from another class, whereas these distributions are wide apart. And the problem is, if I sample a latent vector from here, this does not, or its belongingness to any of the distributions is very, very small. So I cannot really interpolate. Whereas, if I use another constant that all these distributions should be close to a target distribution, then this is the feature space or the latent space that is actually learned by your variational. So here you find that they are very close. So if I take sample a feature vector or latent vector from here, I can easily interpolate from one to other, right? Interpolate in between. And that is how your variational autoencoder works, right? So how do I make the distribution similar? So there comes a concept of KL divergence, pullback Leiber divergence. Okay. So this KL divergence, the expression is given by this. It gives you what is the divergence between two given distributions. Mind you, it is not a distance, because the moment I use something as a distance, it should be symmetric, right? If I compute distance between A and B, so if I say DAB should be same as DBA. So the distance metric, distance should be, if I take some quantity to be a distance metric, it should be symmetric. But when I go for KL divergence, it is not symmetric. You find that KL divergence between QX and PX is QX log QX by PX. If I make it PX QX, the P will come over here, P will come over here, Q will come over here. And these two quantities are not same, right? So I cannot use it for as distance metric, but it's a divergence, and minimization of this divergence will bring the feature clusters, the latent vector clusters of individual classes close to your target class, which is QX, or target distribution. I'll not go further into it. So these are the different cases that we can get. This is an example that I have just shown, that if I use only the data loss, then this is the distribution in the latent space that I get. If I use only KL divergence loss, I don't use the data loss. Then what do you expect? Because I'm not using the data loss, so the class identity of different samples will not be maintained anymore. What I'll get is all the distributions will be similar to your target distribution. So here you find that all the feature vectors, the feature vectors for different classes are shown in different colors. So here you find that all the feature vectors, they are jumbled together in the same space. So I cannot distinguish one from another. If I use both the KL divergence loss and the reconstruction loss together for training my variational encoder, then this is what I get. Okay, so here you find that your distributions are compact. At the same time, you also have been able to maintain the inter-class distinguishability to a reasonable extent. So this is what you get, the latent space that you get after training your variational encoder. Okay, this is how the network will look like. You find that it is similar, the structure is similar to our autoencoder. Okay, so this is the encoder part, this is the decoder part. In case of autoencoder, here what we had was the bottleneck layer, which was giving us the feature vector. Here in there, we are not getting the feature vectors, what we are getting the parameters of the distribution. So as we are using the normal distribution, so for all different classes, we'll get the means and the variances. Okay, so this is what you get from your variational autoencoder. Once I have this distribution, I can sample a vectors Z1, Z2 from this distribution, feed this sample to your decoder. The decoder will be able to generate an output which is similar to the examples that the decoder has seen. Right? It may not be identical to one of them. Right. The aim of using this variational autoencoder or objective is also different from that of autoencoder. We said that in case of autoencoder, once the autoencoder is trained, we were not interested in the decoder part. We were interested in the encoder part because our purpose was to get a feature vector which will be used for classification or recognition. In case of variational autoencoder, we are not interested in the encoder part, but we are interested in the decoder part, because the variational autoencoder, once it is trained, it has learned the distributions. Now my aim is, my objective is that I will sample a latent vector from this distribution, feed it to the decoder, which is now my generator network, and this decoder will give me as output. Right? So once trained, I don't need this encoder anymore. I just need this distribution and decoder. So you find that the objectives in these two cases, they are also different. Okay. This is an example of what this generative model can do. So this was a variational autoencoder, which was trained using the face images which are available in a database known as Celib A database, right? And this database is publicly available. And once the network was trained, then you have the distribution in the latent space. Just sample one point from that distribution, give it to your generator model or the decoder model. The decoder generates the output. And these are the different outputs that were generated from different instances or from different sample vectors. And if you look at this, you'll find that, yeah, and none of them are any image from this particular database. Okay, they are all generated images of synthetic images. And if you look at these images, you find that they're quite natural, right? I mean, it is hardly believable that they're synthetic, but they're actually synthetic, but looks very natural. Right. What are the other things that you can do using this variational autoencoder? You'll find that your object algebra, can also be used in this particular case. So for example, if I take a large number of face images with glasses and train my autoencoder, so I get latent code, so latent code C1. You take another set of face images without glasses, again you find the latent code. Okay, so you find that I have one latent code with glass, another latent code without glass. So if I go for vector difference, I get latent code of a glass only, right? And now I can synthesize an image. I take an image, generate a latent code that you have got for glass. This code, this vector, will fit to your generator. The generator will generate images corresponding to the latent code and this added latent code of the glass, right? The example is this. You have images of gentlemen with glasses. You have images with gentlemen without glasses. Subtract these two vectors. The difference vector gives you the latent code of glass. You have images of women without glass. Add that latent code, the latent code of the glass with this, right? And then you generate the image. The generated images will look like this. So it is quite nice. Then comes what I was talking about is generative adversarial network. Okay, what you do in generative adversarial network is you have, I'll just skip this. Okay. I have a generator part. That is what we just discussed about variational autoencoder, the decoder part of it. And I have a discriminator, and they work in a game theory. The generator generates synthetic images. In this case, we are calling them as fake images. Discriminator tries to discriminate between the synthetic image and the actual image, right? So the discriminator always says the generator, whatever you have generated is rubbish. It is not a real image, but it's a fake image. So that is an error that the discriminator gives. Using this error, the generator is retrained, because my purpose is that the generator has to generate an image which is a real life looking image. So the discriminator should not be able to distinguish between this image and that image. So using this error, again backpropagation, using this error, the generator is retrained so that it becomes stronger and stronger. And the discriminator is also trained at the same time that the discriminator should be able to distinguish between the generated image and the real image. So they are locked in a win-win game. And that is how these two networks are trained together. So these are the different loss functions which are to be used for training the generator and the discriminator. I'll not go into details of this. The loss function for training the generator, which has to be minimized, okay? And this is the loss function used for training the discriminator, right? Once both of them are trained, then you find that they can be used for generating real-like images. So these are the outputs of one such generative adversarial network, and this was presented in ICLR 2018. Similarly, these are other images that can be synthesized. So given a segmented image, something like this, a real image can be generated. Given an input like this can be generated. Input black and white image, a natural looking color image can be generated. Given sketch of an object, a natural looking image can also be generated. So these are the powers of generative adversarial network that you can have. We can use this generative adversarial network for, again, increasing the resolution of images. So there are something called SR-GAN or super resolution GAN. And this is the output from a paper which was presented in CVPR 2016. Here again, another thing, you give the segmented or semantically segmented frames of a scene, you can generate natural looking. So this tells you what is the power of such generative adversarial. Now here I tell you that one of my work with my students, of course, which was presented in 2019 at ISET held in Taiwan. Okay, It is for use of this generative adversarial network for image inpainting. So this was the base paper, which was published in CBPR 2017. We have improved upon it, and we got a paper in ICIF 2019. So here what we have is, say you have a large number of images which are faulty images. So there are certain regions where you don't have image. Now you see that in generative network, how it works. You sample a code, right? You generate an image. Now here, the way this network works is that iteratively, I want to come to a sampled latent vector. So this latent vector will generate an image which is similar to the corrupt image of the faulty image. Okay. So all the remaining part where I have information, this generated image information and that faulty image information, they have to be identical. The error among them should be less. And how the adversarial network comes into picture? It is because I want that whatever image is being synthesized by my generator, that should be a natural. It should not look like a synthetic. Okay. So we have made some improvement on this. So this is different types of loss functions that are used for iteratively changing the sampled value. So gradually you are moving to a particular sample of the latent vector, which will give you a real looking image, which is similar, very, very similar to your input faulty image. I'm not going to details of this, so this was our you find that this is a faulty image, but this information is not available. This is the output of the base paper that I have said. We have shown that is this one, and that this is the output that we have obtained using our approach. And you can easily see that here there is a lot of distortion in the base paper, whereas that distortion is not visible here. Similarly, there is another image where this was a figure 10. This particular work, they could not reconstruct it properly, whereas using our approach, you have been able to reconstruct that figure 10 properly. So these are other things as well. We have also used the same concept for video inpainting. In your video inpainting, the concept was that for the first frame, you get the latent vector, okay, and use the same latent vector as the initial latent vector for the second frame. Okay, and also at the same time, we want that given a number of frames which are very close to each other, the divergence among those frames should not be much, because there should be some spatial consistency. So using this concept, we have developed an algorithm, again, this ICIP, same paper 2019, where our algorithms are 80 times faster than the base algorithm. Just get these videos. This is for a video. This is the output which was given by that base paper, and this is the output that is obtained using our techniques. Okay. So what I mean to say is that this generative adversarial network, where I have both this generative model and the adversarial model, they're very, very powerful tools, not only for generation of new images or new data, and this generation has many applications, right? If I simply use generative model, this generation has a lot of applications, because when I talk about machine learning applications or deep learning applications, you might be knowing that deep learning applications or trained deep learning models is very, very data hungry. And in many cases, you don't have sufficient number of data to train your network. So that sort of data can be generated using your generative network. Okay, so that is a simple example of how this generative network is useful for data generation, which can be used for training deep learning. We have also shown that if you have faulty data, you can use this generative adversarial network to rectify the faulty. Okay, it has many, many other applications. In fact, we ourselves have a number of papers on this, but I cannot discuss all of them in this limited time. Okay, so I stop here. Thank you very much. Let me see, there were some questions, if I can pick up those. Yes, SVM can be used for to differentiate between normal node and abnormal node in ad hoc networking purpose like MANET and WS. Yes, definitely it can be used, because the way you identify a normal node and an abnormal node, that can be converted to a descriptor. And once you have a set of descriptors, definitely SVM can be used. Okay? But when you use SVM, definitely you know there is an added tool that has to be used along with SVM, which is kernel tool, right? Because SVMs are linear machines, so I must have the features which are linearly separable. But in this particular application, the features may not be linearly separable, so you have to use the kernel tools to make the features linearly separable. And once they are linearly separable, you can use SVM for this task. What are different algorithms to differentiate between normal node and abnormal node, and which algorithm better in terms of processing speed? Okay, again, you are talking in terms of MANET and wireless sensor networks. Truly speaking, I'm not expert in MANET and wireless sensor networks, right? So I cannot readily answer this question. Okay. Which algorithm is suitable for image abnormality classification? Okay. This is again a classification task where the discriminative model will work. And you will see that when you go for this machine learning or deep learning techniques applicable to your applications, what is most important is generation of the training vectors or the training samples using which you have to train your network. So when you go for this abnormality detection or abnormality classification, you have to define what is abnormal, right? Say, for example, if I simply talked about an elephant in a jungle, it is not abnormal. But if you have a case that an elephant on the road, in some cases it might be abnormal, in some cases it might not be. If I have a situation like an animal riding a bicycle, okay, talking about circus, it might not be abnormal. But if you talk about normal scenario, your day-to-day scenario, there's abnormal. So firstly, you have to decide that what is abnormality that you are talking about. What is your application domain? Once you decide that, you have to generate a large number of examples, both from abnormal class as well as abnormal class, right? And once you do that, you can train them. There is other approach that I can go for a single class classifier. You might have heard about single class SVM, right? Where you find that your set of abnormalities is infinite. But I can easily generate examples from what is normal as per my requirement. So I can have large number of examples from the normal domain, and anything outside that I can say those are. So I can have a single class support vector machine with some margin where the single class support vector machine is trained with the normal examples, and the support vector machine simply says that if it is not in the normal domain, it is abnormal, right? So what is most important is how do you define abnormality based on your application, and how do you, or most important is how do you generate examples, right? Any other
Sir,
question?
sir, I have one doubt or question like this.
Yeah.
Whether this generative model can be applicable to the handwritten text or
Generation.
kind of Devanagari text like this.
Yes, yes, it can be. Yes. In fact, it is used in many cases. So to train your recognizer, character recognition tasks, you need large number, right? But having such real inputs is very, very difficult. So this generative model, in fact, people has done it. They've used a generative model to synthesize handwritten characters. And those characters are used for training the classifier of the recognizer. Those here. People have used it.
It means that if the text is distorted like this, or then we can train the model distorted
Yes,
one,
yes,
and then
yes, yes.
and then that can be used to reconstruct
People
that,
have done
isn't
it.
it?
People have used it.
Okay, sir. Thank you, sir.
I
Thank
don't
you.
have the reference right now, but there are publications.
Yes, sir. Yes, sir. Thank you, sir.
Any other questions from the participants? You can post in chat box or question answer section, or unmute and ask the sir.
No question in question answer section, ma'am, and even chat box. So I think we can conclude now.
Yes.
Okay, thank you. Thank you all.
Yeah. Thank you, sir. Now I request Dr. Priti Mitange, ma'am, to propose vote of thanks.
Thank you, sir. Prabir Kumar sir has nicely explained the general adversarial network and its applications, how the data can be generated and completed efficiently. And thank you, sir, for spending your valuable time with us. Thank you, participants and one and all. I declare that session is over now officially, and we will meet for the next session after the lunch break at 2:30 p.m. Thank you,
Okay.
sir.
Thank you.
Thank
Thank you.
Thank you, sir.